Welcome back. We are making our way through Chapter 4, Applications of the Derivative, and we have a nice application today in 4.5, Linear Approximation. We will use a line to approximate a complicated function. Here we go. Here is the big idea. A function f is given, like what's drawn on the screen there. And it's easy to compute f of a, suppose, so a is some input to this function, but it's difficult to compute f of b. A good example of this is the square root function. F of x equals the square root of x. It is very easy to compute f of 25, but it's more challenging to compute f of 27. We can make approximations, but what is a good approximation? And so this technique, linear approximation, is a nice way of approximating a function at a point. So I have my function f. I suppose it's easy to compute f of a. It is difficult to compute f of b, and also that b is close to a. So my a would be 25 in this case, and b would be 27. So here's what we do. To approximate f of b, we find a line L of x that's tangent to the function through a f of a. Here's the picture. So through the easy point, I'm going to go up to the curve and draw my tangent line. Then I can compute L of b, because finding the value of a point on a line is really easy. And now the L of b that I found is not too far off from the f of b. So the point on top, that y value, is L of b, and the point on the function itself is actually f of b, those function values. And they're not too far apart. So the big question becomes, what is L of x? What's a formula for that line? And here it is. L of x equals f of a plus f prime of a times the difference x minus a. And this formula comes directly from the point slope formula. Here's a quick justification for that formula. Let's suppose I have a point at x naught, y naught, and a line that goes through that point, and the line has slope m. The point slope formula tells me that y minus y naught equals m times x minus x naught. Now let's suppose that this line is actually a tangent line to a point on a function f. Then maybe this x naught is really a, and the y naught is really f of a. And what is the m? The slope of that line is f prime at a. So my formula becomes y minus y naught, f of a, equals m, f prime of a, times x minus, and what was my x naught? That is the a itself. So y equals f of a plus f prime of a, x minus a. And then finally written as a function of x, this is L of x is f of a plus f prime of a times x minus a. All right, back to the other slides. L of x is called the linear approximation to f of x at x equals a. There are two things I need for the line L. I need the function and I need a point. All right, how about an example? Let f of x equal the square root of x. Let's approximate f of 27. In other words, let's approximate the square root of 27. So looking at my formula, I need a function f. Well, that was given to us. F of x is the square root of x. And I need its derivative. F prime of x equals the derivative of the square root of x, 1 over 2 root x. Now I need f of a. What is a in this problem? And this is where it might be a little tricky. As the problem is stated, there's no a that's given to us. But remember, a is the easy point to plug into the function. I need to just choose something. We're going to make a be 25. So this takes a little guesswork. The problem isn't always going to tell you what a should be, but it's going to be a number that's easy to plug into the function. It's easy to evaluate the function there. F of 25 equals square root 25 equals 5. F prime of 25, 1 over 2 root 25, is 1 over 2 times 5 is 1/10. Now let's write out the line. L of x equals f of a plus f prime of a times x minus a. And that's it. So I have my equation for the line. Let's not forget the original problem. We needed to evaluate the square root of 27. So what I really want is to evaluate that line at 27 now. So L of 27 is 5 plus 1/10 times 27 minus 25. So that's 5 plus 2/10, or simply 5.2. So 5.2 becomes our reasonable approximation for the square root of 27. This linear approximation is kind of a cool technique, right? How far off were we? The last thing we might want to know in a linear approximation problem is the percent error. So in the numerator, we have exact minus approximate, the difference, how far off was I from the real number. And this is the one in the denominator, the one that's easy to forget sometimes. You want the exact answer on the bottom there. So let's say at some later point I find a true exact value for the square root of 27. I can see how close my approximation was. Exact minus the approximation over the exact, absolute of all that times 100%, and 0.074%. So that's pretty good. That's not a bad approximation. It's less than 0.1% off. Okay, you have the tools that you need now to do the homework problems in this section. Don't neglect the worksheet problems. Take a look at those, give those things a try. They'll show you a few different techniques, and ask questions if you have them. All right, good luck.